Welcome to our Bioprocess Engineering online tutorial on fed batch microbial fermentations. Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. In this tutorial, you will explore the fed batch microbial fermentation, one of the most widely used fermentation process in industrial biotechnology. We will address the following key questions. What are the principles of fed batch fermentations? How is the medium feed flow rate determined? What is the maximum cell concentration allowed by oxygen transfer? How can fed batch fermentation be optimally operated to achieve the highest productivity? To illustrate these principles and concepts, we will use the example of microbial cell production, demonstrating how fed batch strategies enhance process efficiency. Industrial microbial fermenters operate in three distinct modes. Batch mode: the entire fermentation medium is introduced at the start, with no further additions or removals during the process. Continuous mode: fresh medium is continuously fed into the fermenter, while an equal amount of culture is simultaneously withdrawn. Fed batch or semi-continuous mode: a portion of the medium is added initially, and the remaining part is gradually fed over time without removing culture. The choice of the optimal fermentation mode depends on the specific microbial transformation being performed, as each approach offers advantages for different processes. The fed batch process serves as an intermediate mode between batch and continuous fermentation. The fermenter is initially partially filled with a starting medium before being inoculated with microbial cells. The process begins with a batch phase, allowing cells to adapt to their new environment and multiply. Once this phase is complete, a continuous flow of feed medium is gradually introduced into the fermenter without removing any culture. The medium feed flow rate is carefully controlled to maintain relatively low nutrient substrates concentrations. The feeding process continues until the fermenter reaches its maximum working volume, at which point medium addition is stopped. Fed batch fermentations are typically conducted under prolonged nutrient limitation, most commonly by controlling the carbon source concentration. However, other essential nutrients, such as nitrogen and phosphorus, can also be limited to optimize microbial growth and metabolism. Operating under substrate limitation or reduced growth rates offers several key advantages. Minimized metabolic overflow. It reduces the accumulation of unwanted byproducts associated with rapid growth. Enhanced production of non-growth associated metabolites. Many industrially valuable compounds, such as secondary metabolites, are produced more efficiently under nutrient-limited conditions. Lower oxygen demand. It helps prevent oxygen limitations that can occur at high biomass concentrations. By carefully managing nutrient supply, fed batch fermentation maximizes productivity and process efficiency. Fed batch fermentations are more complex to operate and optimize compared to batch or continuous processes. The complexity stems from several factors. Increasing medium volume. As the fermentation progresses, the volume of medium in the fermenter increases, which can dilute both biomass and product, affecting the overall process efficiency. Variable medium flow rate. In a fed batch operation, the feeding flow rate is typically adjusted based on cell concentration and metabolic activity. This adjustment ensures that nutrient concentrations remain relatively constant throughout the fermentation process. Multiple operational variables. The process involves several key variables, including the initial volume fraction and medium composition, and the composition of the feed medium, all of which need careful management. The fed batch process must be specifically tailored to the kinetic characteristics of the particular cell line used to ensure optimal performance. In this tutorial, the fed batch operation and optimization strategy are demonstrated using a fermentation process that involves the growth of bacteria on a sugar substrate. The fermentation takes place in a 1,000-liter, stirred and aerated industrial fermenter. The optimal fed batch operation strategy is investigated using a simulation model of the fermentation process. This knowledge model incorporates the rate-limiting factors of bacterial growth and metabolism, as well as oxygen transfer. The simulation model, acting as a digital twin of the fermentation, enables the virtual operation of fed batch fermentations under various conditions. This approach helps to better understand and assess the impact of different operational variables and provides valuable insights for optimizing these variables to maximize fermenter productivity. When designing fed batch fermentations, the first step is to determine the appropriate medium feeding flow rate to be applied throughout the fermentation process. For example, let's consider a scenario where the fermentation starts with an initial medium volume fraction, V0 over Vt of 0.5 in the fermenter, an initial sugar concentration S0 of 2 grams per liter, and an inoculum concentration of 1 gram per liter of bacterial biomass. After a few hours, medium with a sugar concentration S feed is continuously fed into the fermenter. The medium flow rate Q is then adjusted instantaneously to maintain a constant steady-state sugar concentration SSS throughout the fermentation process. This steady-state sugar concentration is in the range of 0.1 to 0.5 gram per liter. The question is, what is the required medium flow rate Q to maintain this steady-state sugar concentration during the fed batch operation? The required medium flow rate during fed batch fermentation is influenced by the kinetics of cells' growth and metabolism. Microbial cell kinetics refers to the set of laws that describe the specific rates of cell growth, sugar consumption, and oxygen consumption as a function of medium composition. The most commonly used model for bacterial growth kinetics suggests that the growth rate reaches a maximum at high sugar concentrations and decreases when sugar becomes limited. According to the Monod rate law, the specific growth rate mu is given by mu equals mu max S over Ks plus S, where mu max is the maximum specific growth rate, S is the sugar concentration, and Ks the half saturation constant. The specific sugar consumption rate, Qs, in grams sugar per gram of biomass per hour is typically proportional to the cell's specific growth rate, with a stoichiometric coefficient Ys over X in grams sugar consumed per gram biomass produced. Similarly, the specific oxygen consumption rate, QO2, in gram oxygen per gram of biomass per hour is also proportional to the cell's specific growth rate, with a stoichiometric coefficient YO2 over X in gram oxygen consumed per gram biomass produced. For the bacterial strain used in the fermentation simulation, the kinetic law's parameters are as follows. Mu max equals 0.5 hour minus 1, Ks equals 0.4 gram per liter, Ys over X equals 2 grams sugar per gram biomass, and YO2 over X equals 0.75 gram oxygen per gram biomass. To determine the optimal medium feeding flow rate, the first step is to analyze cellular growth dynamics during the fed batch process. Since during fed batch fermentation, both the medium volume V and biomass concentration X increase over time, it is more pertinent to consider the total biomass mass Mx in the fermenter, which is the product of the volume V and the biomass concentration X. The time variation of the cellular mass Mx is described by the instantaneous mass balance for the cells in the fermenter. In the absence of inlet and outlet terms, the instantaneous balance in gram of biomass per hour is given by Rx equals dmx over dt, where Rx is the rate of biomass production in the fermenter, and dmx over dt is the rate of variation in cellular mass. The biomass production rate Rx is equal to the product of the specific growth rate mu, the biomass concentration x, and the medium volume V, or alternatively, Rx equals mu mx. At the constant steady-state sugar concentration SSS, the specific growth rate is constant at mu SS, and the resulting differential equation is mu SS mx equals dmx over dt. This equation is integrated to yield the time increase in the cellular mass, mx equals mx0, exponential mu SS t, where mx0 is the initial biomass mass. This equation describes the exponential increase in cellular mass over time during the fed batch fermentation process. The required medium flow rate to sustain the exponential increase in cellular mass is determined from the instantaneous sugar mass balance in the fermenter, expressed in grams of sugar per hour. Q, S feed minus RS equals dms over dt, where QS feed is the inlet sugar feeding rate, RS is the sugar consumption rate in the fermenter, and dms over dt is the variation rate of the sugar mass in the fermenter. Under steady-state conditions for the sugar concentration, the variation rate term is 0, and the balance relation simplifies to QS feed equals RS. Accordingly, at each moment the sugar feeding rate must be equal to the sugar consumption rate. The sugar consumption rate RS is equal to the product of the specific sugar consumption rate QS, the biomass concentration X, and the medium volume V, or alternatively, RS equals QS mx. At the steady-state sugar concentration SSS, the specific sugar consumption rate QS is given by the product of the stoichiometric coefficient YSX and the steady-state specific growth rate mu SS. Consequently, the total sugar consumption rate RS is expressed as RS equals YS over X, mu SS, mx0, exponential mu SS, t. This indicates that the sugar consumption rate increases exponentially throughout the fed batch fermentation. Consequently, to sustain the exponential increase in cellular mass, the sugar feeding rate to the fermenter must also follow an exponential increase. The required volumetric medium flow rate Q, in liters per hour, is determined by dividing the previously calculated sugar feeding rate by the feed sugar concentration S feed. Q equals YS over X, mu SS, mx0, exponential mu SS, T, divided by S feed. To express the feeding flow rate relative to the total fermenter volume, the volumetric feeding flow rate, Q over VT, is introduced by dividing Q by the total fermenter volume, VT. Q over VT equals YS over X, mu SS, V0 over VT, X0, exponential mu SS, T divided by S feed. This equation shows that the volumetric flow rate Q over VT increases exponentially during the fed batch fermentation. It is influenced by the initial medium volume fraction V0 over VT, the inoculated cell concentration X0, the steady-state sugar concentration SSS, and the feed sugar concentration S feed. With a controlled exponentially increasing flow rate, the kinetics of the bacteria fed batch fermentation is illustrated for a feed sugar concentration of 100 grams per liter and a steady-state sugar concentration SSS of 0.2 gram per liter. Starting from an initial medium volume fraction, V0 over VT, of 0.5, the medium volume fraction V over VT increases steadily until it reaches the final value of 1 when the entire fermenter volume is filled. Simultaneously, the biomass concentration X increases, eventually reaching a final concentration X fin near 26 grams per liter. Using the exponential growth relationship for the cellular mass in the fermenter, the time T-fin required to fill the fermenter and achieve the final biomass concentration X-fin can be calculated as T-fin equals 1 over mu SS logarithm VTX-fin over V0X0. In the scenario considered, the final fermentation time is approximately 24 hours. The previous fed batch fermentation kinetics were established under the assumption that there are no limitations due to oxygen transfer. In reality, however, the fermentation kinetics can be influenced or limited by the rate of oxygen transfer, in addition to the cell kinetics. In a continuously aerated fermenter, oxygen is constantly transferred from the air phase to the liquid medium. As the cells consume oxygen, the dissolved oxygen concentration decreases below its solubility. Concomitantly to the cell concentration increases, the rate of oxygen consumption also rises, causing the dissolved oxygen concentration to steadily decrease. If dissolved oxygen drops below a critical threshold, the growth rate becomes oxygen limited, potentially leading to the induction of metabolite excretion. Modeling the influence of oxygen transfer limitations is based on the principles of oxygen solubility and oxygen transfer rate. The solubility of oxygen O2 star, expressed in grams of oxygen per liter, is calculated as the partial pressure of oxygen PO2 in atmospheres, divided by Henry's constant KO2, which has units of atmosphere liter per gram. The partial pressure of oxygen PO2 in air is the product of the oxygen mole fraction YO2 and the total pressure P. Oxygen transfer between the air and the liquid medium is primarily limited by the transfer of oxygen from the first liquid layer at the air-liquid interface, which is saturated with oxygen, to the bulk liquid medium where the dissolved oxygen concentration is O2L. The rate of oxygen transfer, JO2, in grams of oxygen per hour is described by the mass transfer law, JO2 equals KLA, O2 star minus O2L, V, where KLA is the volumetric oxygen transfer coefficient of the fermenter, which is the product of the oxygen transfer coefficient KL in the liquid medium and the interfacial air surface area A in square meters per cubic meter medium. To better understand the impact of oxygen transfer limitations on fermenter efficiency, it is useful to introduce the concept of the maximum oxygen transfer rate. For a given aeration capacity KLA, the volumetric oxygen transfer rate, JO2, reaches its maximum value when the difference between the oxygen solubility, O2 star, and the dissolved oxygen concentration, O2L, is at its highest. That is when O2L is 0. However, in practice, it is preferable to maintain the dissolved oxygen concentration above a critical minimum value, O2L min, to prevent a reduction in the growth rate or the accumulation of undesirable metabolites. In this context, the maximum oxygen transfer rate is reached when the dissolved oxygen concentration is equal to O2L min. Thus, the maximum oxygen transfer rate, denoted as JO2 max, is expressed by the following relationship. JO2 max equals KLA, O2 star, minus O2L min, V. During fed batch fermentation, the oxygen molar fraction in the outlet decreases due to the increasing oxygen consumption rate in the fermenter. This leads to a gradual decline in the mean oxygen solubility in the fermenter. As a result, the maximum oxygen transfer rate, JO2 max, decreases slightly over the course of the fed batch fermentation. The dissolved oxygen concentration in the fermentation medium is calculated from the instantaneous oxygen mass balance on the liquid phase. This balance takes into account that oxygen is continuously transferred from the air to the liquid medium at the rate JO2 and consumed by the cells at the rate RO2. The oxygen mass balance equation is JO2 minus RO2 equals dMO2 over dt. Due to the very low oxygen solubility, the variation rate term dMO2 over dt is negligible. Therefore, the oxygen balance simplifies to JO2 equals RO2. Thus, at any given moment during fermentation, a quasi-steady state is established in the liquid medium. The oxygen transfer rate JO2 matches the cellular oxygen consumption rate RO2. The equality between the oxygen transfer rate JO2 and the oxygen consumption rate RO2 can be maintained as long as RO2 is smaller than the maximum oxygen transfer rate JO2 max. During the fed batch fermentation, the oxygen consumption rate increases as the cellular mass in the fermenter rises. The maximum value of RO2 is reached when the oxygen consumption rate becomes equal to the maximum oxygen transfer rate, JO2 max. Under these conditions, the dissolved oxygen concentration O2L drops to the critical dissolved oxygen concentration O2L min. In this case study, the 1,000-liter fermenter operates at an overhead pressure, P out of 1.5 atmosphere, to enhance oxygen solubility. By the end of the fed batch process, when the fermenter is fully filled, the air inlet pressure, P in, reaches approximately 1.7 atmospheres. Under these conditions, the mean oxygen solubility, O2 star in the medium, is 10.5 milligrams per liter. The fermenter has a volumetric oxygen transfer coefficient, KLA, of 400 hours minus 1. For a critical dissolved oxygen concentration, O2L min, of 2 milligrams per liter, the maximum oxygen transfer and consumption rates are approximately 3.5 grams oxygen per liter per hour. For cells growing at the steady-state specific growth rate, μSS, the maximal oxygen consumption rate, RO2 max, is related to the maximal cell concentration X max by the equation RO2 max equals QO2 X max V equals YO2 over X μSS X max V. The maximum cell concentration allowed by oxygen transfer, denoted as X max O2, is reached when the oxygen consumption rate is at its maximum, equal to the maximum oxygen transfer rate, JO2 max. Therefore, X max O2 equals JO2 max, divided by YO2 over X mu SS V. This relation shows that the maximum biomass concentration, allowed by the oxygen transfer rate, is inversely proportional to the cell-specific growth rate. In this case study, at the steady growth rate, μSS of 0.17 hour minus 1, the maximum biomass concentration is near 27 grams per liter. The third part of the presentation focuses on the optimal operation of the fed batch fermentation, considering the limitations imposed by oxygen transfer on the cellular biomass concentration. The most common optimization criterion for fermentation processes is the production cost per kilogram of product. The production cost is primarily influenced by the fermenter's productivity. In the case of cellular biomass production, the productivity prod X, expressed in grams of biomass per liter per hour, is calculated as the mass of produced biomass divided by the fermenter volume and the fermentation duration. At the final fermentation time T-fin, when the fermenter is filled with medium, the productivity is calculated as the final biomass concentration X-fin divided by the fermentation time T-fin. In this form, productivity represents the hourly efficiency of fermenter equipment utilization. The investigated optimization strategy aims to achieve the highest possible fermenter productivity prod X at the end of the fed batch fermentation. The fed batch fermentation is conducted using the previously determined exponentially increasing medium flow rate to maintain a low steady-state sugar concentration. The optimization of the fermentation involves 4 operational variables: the initial volume fraction V0 over Vt, and sugar concentration S0, the feed and steady-state sugar concentrations S-feed and SSS. Among these, the initial sugar concentration S0 is the least critical variable and is set slightly above the steady-state sugar concentration SSS. In this case study, it is set at 2 grams per liter. The initial volume fraction V0 over Vt is carefully adjusted to ensure that the maximal cell concentration allowed by oxygen transfer is reached by the time the fermenter is completely filled. The steady-state sugar concentration SSS and the feed sugar concentration S-feed are optimized to maximize fermenter productivity. At a fixed sugar feed concentration and steady-state sugar concentration, there exists an optimal intermediate initial volume fraction, V0 over Vt, that maximizes fermenter productivity. This optimal V0 over Vt can be explained as follows. When V0 over Vt is too low, the volume of medium to be added and the fermentation time are too long. Under these conditions, the maximum biomass concentration, Xmax O2, allowed by oxygen transfer, is reached before the fermenter is completely filled. As a result, the fermenter operates less efficiently, leading to reduced productivity. At a high initial medium volume fraction, the volume of medium to be added is small. As a result, the fermenter reaches its full volume before the maximum biomass concentration, Xmax O2, allowed by oxygen transfer is achieved. Under these conditions, the fermenter's aeration capacity is not utilized efficiently, leading to reduced productivity. At the optimal initial medium volume fraction, the fermenter reaches full capacity just as the maximum biomass concentration, Xmax O2, allowed by oxygen transfer is achieved. This ensures the most efficient use of the fermenter and maximizes productivity. To ensure that the fermenter filling time T-fin coincides with the moment when the maximum oxygen transfer rate is reached, the initial medium volume fraction V0 over Vt must be carefully adjusted. Specifically, the initial medium volume V0 is set so that the total amount of sugar added during the fermentation matches the sugar mass required for the expected biomass production. The total mass of added sugar, MS add, consists of the initial sugar mass, V0S0, and the sugar supplied during feeding, Vt minus V0, S-feed. The total sugar mass required for biomass production is given by the stoichiometric coefficient Ys over X, multiplied by the total cellular mass produced by the end of fermentation. By equating these two sugar mass expressions, the required initial medium volume fraction, V0 over Vt, can be determined. Neglecting the contributions of the initial sugar and biomass, this relationship is V0 over Vt equals 1 minus Ys over X, X max O2, divided by S-feed. According to this relation, the optimal V0 over Vt depends on the feed sugar concentration. A higher S-feed allows for a higher V0 over Vt. When X-fin is the maximal X max O2 allowed by oxygen transfer, the initial volume fraction V0 over Vt is also influenced by the cell-specific growth rate, which is governed by the steady-state sugar concentration. What is the optimal sugar feed concentration? The highest fermenter productivity is achieved at the highest feasible sugar feed concentration, S-feed. While S-feed does not directly influence microbial growth rate, it affects the rate at which the medium volume increases during fed batch fermentation. A higher S-feed increases the initial volume fraction, V0 over Vt, minimizing the dilution effect caused by the expanding medium volume. As a result, biomass concentration rises more rapidly over time. Therefore, to maximize fermenter productivity, the highest practical sugar feed concentration should be used. The most critical operational variable to optimize in fed batch fermentation is the steady-state sugar concentration, SSS. This parameter directly regulates the specific growth rate, μSS, and determines the maximum biomass concentration, Xmax02, permitted by oxygen transfer constraints. At a fixed initial volume fraction and sugar feed concentration, there is an optimal intermediate range of SSS values that yields the highest fermenter productivity. This can be explained as follows. Lowering SSS reduces the specific oxygen consumption rate of the cells, allowing a higher final biomass concentration, Xmax02. However, a lower SSS also slows the specific growth rate, thereby extending the final fermentation time fin. As a result, the fermenter productivity, calculated as the maximum biomass concentration, Xmax02, divided by the final fermentation time T-fin, exhibits an optimal intermediate range for SSS, rather than being maximized at its lowest value. This aligns with a common observation in fermentation processes. The highest productivity is not achieved under conditions that maximize final product concentration. Following the previously outlined optimization strategy, the optimal operating variables for this 1,000-liter fermenter in the bacterial fed batch production are: initial sugar concentration equals 2 grams per liter, initial medium volume fraction equals 0.85, feed sugar concentration equals 300 grams per liter, steady-state sugar concentration equals 0.25 gram per liter. Under these optimized conditions, the volumetric feeding flow rate increases exponentially, reaching a maximum of 0.03 liter per hour. After 17 hours of fermentation, the fermenter is fully filled. The cell concentration reaches the final biomass concentration of 24 grams per liter, which is limited by oxygen transfer capacity, and the highest fermenter productivity achieved is approximately 1 gram per liter per hour. In this tutorial, you explored the key principles of fed batch fermentation for microbial cells production. You learned how to implement an exponentially increasing medium flow rate to maintain a constant sugar concentration throughout the fed batch process. Determine the maximum biomass concentration limited by the oxygen transfer rate. Optimize fed batch operational variables to achieve the highest fermenter productivity. If interested, you can gain a deeper insight in microbial fermentations by enrolling to one of our 2 online courses: Microbial Fermentation Processes, Optimize Fermenters Operations, and Simulation, Scale-Up, and Optimal Operation of Microbial Fermentations. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.